Alright, so this is going to be the third part of our review. So first question, just asking us what does a particular derivative mean? What is the best interpretation of c prime of 3 equals 500? And so for me, I always just like to come back and say, okay, well, I know that the derivative is the slope at a point, the instantaneous rate of change. And we know that slope is change in y over change in x. So what are the units for y and what are the units for x? And in this case, they tell us that the total number of pieces of candy, that's my y, so this is candy, and then the input is since it opened, or the number of hours since the factory opened. So then this is hours. So the meaning of my derivative is just some version of candy per hour. And as I read this, each of these, the first one, the factory produces 500 pieces of candy. Well, that's not a rate. I need it to be per hour. So that's out. No. Produces 500 pieces of candy in the first 3 hours. Again, that's not a rate. My derivative should be a rate, something per something, candy per hours in this case. The rate at which the candy is producing or at which the factory is producing candy is increasing at a rate of 500 pieces per hour, 3 hours after it opens. So that's closer because at least it's a rate, but that's pieces of candy per hour. That's putting another per hour into here, which is not what's happening. That would be the second derivative. So that's, again, no, leaving with only the last one. Let's make sure it makes sense, though. The factory is producing candy at a rate of 500 pieces per hour. Hey, that's candy per hours, yes. 3 hours after it opens. That's the key to a derivative, is that this rate is at a particular time, not for the first 3 hours, not during the third hour, but at time t equals 3. So that's exactly what the derivative means. Very nice. Next problem. Okay, we have our position function, and we want to know what is when is the particle at rest. Well, we are at rest when v of t, the velocity, equals 0. So first I need to find v of t and then just figure out when it's 0. They give us position, so I need to take the derivative to get to velocity. Nice little power rule here. 6t squared minus 42t plus 72. I can set that equal to 0. I'm also going to divide out a 6 and get t squared minus 7t plus 12. That factors nicely. T minus 4, t minus 3. So the velocity would be 0 both when t equals 3 and when t equals 4. And if the velocity is 0, then the particle is at rest. Another position one here. Okay, we're given position, and we will need to know the acceleration. So then I need the second derivative, because acceleration is the second derivative of position. So first, let's find velocity, which is the first derivative of position. Now, we need to do actually some chain rule here, because we have the 2 and the 3 inside of these things. So let's go ahead and show the chain rule. Why not? So I'm just going to do on the side y equals sine of 2t. I take the inside, I call that u, and the outside I leave as y. And so now it's sine of u. The key here, where many of us struggled earlier in the year when we were first learning about chain rule, is we would forget to make this a u, but it has to be a u because this function y must be equivalent to this function y. They're both y, they have to be the same. So they are the same because u equals 2t, and so I can write u instead of 2t because I have stated that they are the same. If I call this t, I'm wrong. y does not equal sine of t, y equals sine of 2t. But y does equal sine of u because u does equal 2t. Then I take the derivative of each piece, du dt equals 2, dy du equals cosine of u. Multiply those two things together, dy dt is going to equal 2 cosine, and I can't leave that as cosine of u, I have to substitute back, so I'm going to do that all in one step and make that cosine of 2t, because u, again, is equal to 2t. More or less the same thing will happen in the other part, so I'm going to skip that. I'm going to leave that to you because that's not really the focus of this problem. So we've got 2 cosine 2t, and this is going to become plus 3 sine of 3t. Running out of room, sorry. Now I need the second derivative. I need the acceleration. So a of t is going to equal x double prime, which is going to be negative 4 sine of t, or sorry, sine of 2t, plus 9 cosine of 3t. Again, just using that chain rule, be careful with your sines and cosines and their pluses and minuses when doing the derivative. And they want us to plug in pi here. And when you plug in pi, I believe, if my math is correct, you're going to get negative 9. All right. Another one of these position, velocity, acceleration questions. In this case, they're asking when is the speed increasing? For what values of t is the speed increasing? And there's a couple different ways you can answer that question, but the way that we focused on it, the way that's sort of most transferable, works in the most situations for us, is to remember that speed is increasing if both velocity and acceleration have the same sign. And so first thing I need to do, of course, and we'll look at, I have a graph down here, we'll look at that in a minute. But first I have to actually figure out what is the acceleration function. They gave me velocity, so that was nice. So a of t is, of course, just the derivative of that. Little power rule to start. Negative 3t squared plus 4t. I think I might need a little more room. And then got to use chain rule again here, and remember the rule for the exponential. This is going to be minus 2 to the negative t times ln of 2. That's just the rule for the derivative when it's of an exponential when it's not e to the x. It's whatever that thing is, so 2 to the t times ln of that base. And then because there's a minus in that exponent, technically I have a chain rule there, which is what gives me the minus out here. So then, looking at this, what I need to do is I need to figure out, where are the critical numbers, where is this 0 or undefined, so that I know where it might cross over the x-axis. Same with this acceleration. In this case, I can't factor or do anything nice algebraically, so I just graphed it. Mine's, of course, from Desmos, so that I can put it on here, but you should be able to do this on your calculator. And I'm just looking for where the two graphs have the same sign. I can see that acceleration is positive only in this little bump, and then it's negative for the other parts. Velocity is positive everywhere except after this x-intercept here. So they're both positive in between here, which is actually these values here. And then they're both negative after this value here, because once I hit that, then the velocity is negative, and then of course the acceleration has been negative for a while. So that's this one there. All right, moving on. All right, the base of a triangle is decreasing at a given rate. The base is increasing at a given rate. The height is decreasing at a given rate. Which of the following must be true about the area of the triangle? Well, they're asking us, okay, is it increasing? Is it decreasing? What's the deal here? So basically, what they're asking me about is the rate of change of the area. They're asking me about dA dt. And I know dB dt is 3, and dH dt is -3 because it's decreasing. So if I set up my equation here to figure out dA dt, A is of course 1/2 base times height. The derivative there, I've got to use product rule. I'm going to sort of treat it as if the 1/2 is attached to the B. That way I don't have to treat it as 3 separate pieces, 1/2 times B times H. I can just say, oh, it's 1/2 B times H. And that'll make my product rule simpler to deal with. So then I'm going to leave the 1/2 B alone. And then the derivative of H is just dH dt. Now, take the derivative of the 1/2 B, and that's 1/2 dB dt. Leave the H alone. Now we are told these different rates here. So we go ahead and plug those in. dA dt is going to be -3/2b plus 3/2h. Just plugging in the 3 and the -3 and then combining that with the 1/2. I'm not given values for b or h. Usually in a problem like this we would be given a value for a b and an h, and then we plug in and we find a particular dA dt. But that's not the case here. Here they're just saying, okay, well, is dA dt increasing, decreasing, constant? When is it increasing? When is it decreasing? And so I'm going to simplify this a little bit. I'm going to factor out the 3/2. And then I'm going to rearrange it to be h minus b. I think that's a little easier to see what's happening here, because the h is positive and the b is negative, and I could keep it as -b plus h, but it's easier for my brain to think about it as h minus b. Obviously, this thing will be positive as long as h is bigger than b, and thus it will be negative anytime that b is bigger than h. So, well, and actually I'm maybe getting a little bit ahead of myself there. First of all, dA dt does not always remain constant. It's going to change. This is not, there's no reason that this would be always constant. You plug in different values for h and b, and dA dt is going to be either positive or negative. Only if h equals b would dA dt be 0 and thus a be constant, which is not the case here. So it's certainly not always a constant. A is always increasing. Well, again, dA dt is not always going to be positive. It's going to depend on the relationship between h and b. So it's not always increasing. It's not always decreasing. So which is it here? Decreasing when b is bigger than h. So if b is bigger than h, h minus b will be negative. Yes, that seems to be correct. Let's double check. Decreasing when b is less than h. No, that obviously can't be true. It's the opposite of what we just selected. All right. Similar problem here. This is another related rates. This time we're talking about the area of a circle. And we're given dr dt increasing, so it's a positive. We want to know dA dt. And so we just say, okay, well, what's the relationship here so we can relate these rates? Well, A is equal to pi r squared. Derivative of that, dr dt is equal to 2 pi r, oops, sorry, this is dA dt, 2 pi r dr dt. I'm looking for dA dt, so I want that to be blank. I have dr dt, so that's nice. So 2 pi r dr dt is 0.2. Now the problem, they didn't tell me r, they told me c. They said when the circumference is 20 pi. Well, I can find r easily enough given c, right? c is equal to 2 pi r. 20 pi is what they gave us. So then 10 is equal to r. Plug that in. And we're going to get 4 pi. And then the units here are, of course, meters squared per second. I didn't include the units in my math, but I know that area is measured in meters squared, and it's changing with respect to time, which they told us here is in meters per second, or is in seconds. All right, last one before we'll take a break and start another video. They're talking about a tangent line here. Anytime I'm seeing a tangent line, I'm going to jump right in and I'm going to say, okay, y minus y1 is equal to m times x minus x1. And it's the tangent line at x equals 2. So my x1 is going to be 2. Now I need to know what's the y that goes with that. Well, f of 2, when I input 2, I get out 1. And f prime of 2, the slope at x equals 2, is 4. And then I'm just supposed to approximate the value of f of 1.9 using this tangent line. So I wrote the equation of the tangent line. Now I simply plug in 1.9 into that equation. And when I do that, I believe I get 0.6. All right. They did give us this piece about f double prime. Actually not relevant here. Sometimes in a question like this, they're going to ask you, is this an underestimate or an overestimate? And that's where this would be important. Because the second derivative is 3, which is positive, my graph will be concave up. And anytime the graph is concave up, the tangent line will be underneath the graph. Didn't end up mattering here, but we are reviewing, so nice to point that out. All right.